Hello, hello, hello. Awesome. Cool. So you just heard about FHE, so I'm going to be talking about the other side of the equation, so ZK and MPC. And to answer, I forget the panelist's name, but to answer the question of like why ZK and FHE were sort of put against that is like crypto people are like really hyped on trends and like they usually want to follow a trend. So when you hear about privacy and you have like one technology does privacy, the other technology does privacy, it's like very easy to put them against each other even though they have different properties and have different application use cases. But yeah, really great panel. Thank you guys. It was really awesome. So today I'm going to be talking about privacy for the world. It's a pun in the name of our company or our project. And sort of talking about the state of client-side proving. So this is going to be a more technical version of my EthCC talk that I gave on Monday, which was named or titled Privacy and Identity at Scale. So I'm DCBuilder. I'm a research engineer at the World Foundation, where I mostly work on like coordinating things around client-side proving or applied cryptography, programmable cryptography, and the intersection with identity. So I work with partners, and I sort of like try and help decentralize the project and onboard other people to sort of build in the sort of privacy-preserving identity ecosystem. So what is World? Maybe you've known us before under the name of WorldCoin. We rebranded in October of last year. But World has four main products, just as a prequel to like what I'm going to be talking about. So World app is sort of our front end or client, a mobile app that is gives people access to our network, which we're building. We're trying to build the largest financial and identity network in the world. And you can interact with our wallet, which is part of the World app, through the application. And you can also interact with World ID. World ID is our privacy-preserving proof of personhood protocol. So maybe if you've been at EthCC in the fourth floor, we have this orb, which allows you to verify that you're a unique and real human being. And then using ZK and cryptography, you can prove that to other people. We call them relying parties. We also have WorldChain, which is an OP stack L2 on Ethereum, and WorldCoin, which is the asset that we fairly distribute to people just on the basis of them being unique humans. So every person is proving they're unique human on sign up and every month so that you know like that the person sort of claiming this token is a unique human. So these are sort of like some of the main components. This is what World ID looks like. World ID essentially is a tab, right? You have three tabs. I only showed the World ID one, but you have the mini apps, which is like third-party applications people can build for our users. You have the wallet, and then you have World ID. And one of the things that is really exciting about World ID is that now we're moving not just on, not doing just proof of personhood, but we're trying to expand the sort of realm of your identity you can create proofs about, right? So some of the data that we have around like our users, so like conceptualize like our growth and user base, we have about 13.4 million users that have been verified by the orb around 160 countries globally. 28.8 million users across like just like general downloads of the World app across iOS and Android. 1.6 million daily transactions on WorldChain, and over 600 million tokens. There's lots of other metrics I could talk about, but I would like to get into the meat of it. Another thing is that everything we build is open source. So from the orb hardware to the firmware, the biometrics, cryptography, all of the things that we do end to end, the protocol is open source. So if you are ever curious, feel free to check out our GitHub. So the main topic that I wanted to talk about is client-side proving and why it's important. The client-side proving paradigm is necessary because like whenever you have a part of your identity that is private, so let's say, I don't know, like your financial history or things like your personal identity, like your KYC documents or your browsing history, anything that like sort of conveys parts about you that like are sensitive or important to you. If you want to create a proof of that information or like selectively choose like, hey, I want to prove to another party that I'm over 18. I want to prove to someone that I'm a person. I want to prove to someone that I don't know, like I have more than $1,000 in a bank account. Things like that. I do not want to share my personal data with a third party. I always want to create the proof in my own local device. And this means that you need to create you need to run these ZK systems on either mobile devices, because most of the applications that nowadays people use are in mobile apps across iOS and Android and other ecosystems, or on a sort of like personal computer paradigm, right? So like Mac OS or Windows, right? Like, or Linux, right? So there's two main like consumer platforms that people use, either PC or mobile. And so client-side proving just means that we're running these ZK systems in these devices, as opposed to like server-side proving. If you've been familiar with the ZK rollup space, ZK rollups, they're not, this has been a common misnomer, like they're not actually zero knowledge, they're just like validity rollups where you prove the state transitions, but there's nothing private. And now they call ZK rollups the ones that are actually private, which is funny. But yeah, like essentially now we actually have to keep state private, and the state is the state of the user. It's not just a public blockchain. So we actually need to create these proofs on a lower device, on a low end, like hardware mobile device usually. And so we've been building applications for tens of millions of users, and we've seen what a production application actually needs, right? When it comes to the requirements, like what sort of phones people have out there on a global scale. You have usually like an old phone from like 2013 with like 2 gigs of RAM, very low performance, like an old CPU, old instruction sets or ISAs, like something that is like really painful to work with, right? People don't have a lot of mobile data, so you also cannot delegate the work to a server and do some like MPC, ZK, like we call this collaborative snarks or co-snarks. You just essentially have a lot of constraints because you're running these provers, these ZK circuits, these ZK provers on low-end hardware. So this has been something that we've like tried to work with as a constraint. And some of the goals that we have is that the 99th percentile of world app users should be able to create these proofs of arbitrary statements about their identity. Another one that we have is on-chain verifiability, right? Since we create like a lot of these proofs, currently it's on the order of like 10 million to 20 million proofs per month for a personhood, right? Like these world ID proofs that we create. And if you, like one ZK proof verification on the EVM is like 200,000 gas, you can really like see that like if you scale this by like 1 or 2 orders of magnitude, there's not enough gas on like even the state-of-the-art L2s to even verify all of these proofs. So one of the problems is that you need to sort of make all of these proofs on-chain verifiable and also be aware of the scale. Like if you're actually going to 100x the use cases, then you're going to probably like 1,000x the demand for proving. Therefore, you need to also like have that in mind when it comes to on-chain verifiability. Currently, most people use Groth16, which is sort of like the most popular proving system because it's EVM friendly. It's subsidized by the EVM through precompiles because you can verify these elliptic curve pairings. But yeah, this is sort of like another constraint. The next one is more of on like a product side, right? So I showed you the render earlier, right, around what World ID looks like. It needs to be a UI that every person that you meet on the street should be able to use. The problem with a lot of crypto applications is that they may be made for crypto natives, but when it comes to a normal person actually getting a use out of it, it's quite hard to make intuitive UIs and also a user experience that doesn't make them wait like a minute to generate a ZK proof. Because the user just like is used to like using TikTok and like instantly like swiping and things being like real time. So essentially when you're trying to build an application, you need to work with that as a constraint as well. Another thing that we really care about is that the tools that we build should not be just usable by us and the protocols that we're building, but they should be like something that is generic and generally like usable for any other use case outside of World. So for that, I'll talk about like why we chose the things that we did. But this is another constraint, right? You need to have a set of APIs and programmer toolkits, like developer tools that people want to use and people can extend, like modularize, they can swap in their different components, which also ties into developer experience, right? Like people need to have a set of APIs that feel intuitive to build like privacy preserving applications with. So this is sort of like why we introduced ProofKit. We're building this tool that allows you to essentially build the most performant client-side proofs you can. And what it is, it's a backend for the Noir programming language. So Noir is a zero-knowledge domain-specific language, or DSL, built by the Aztec team. Aztec is building a privacy layer 2, and there is a big ecosystem around Noir for writing zero-knowledge circuits. And it's sort of been like this golden standard for like DSLs nowadays. Like a lot of the teams like ZK Email and others who have like been building a lot of the infrastructure, cryptographic libraries, applications, and such have mostly been built on Noir. And it's been sort of like the most friendly sort of developer ecosystem that we found where we could like actually contribute. And also for us, the Noir compiler was like very well designed, modularized enough to the point where we can like get a team of cryptographers, compiler engineers, and cryptography engineers to actually build around it and build our own backend. So what it allows you to do is for any Noir circuit that anyone has ever written. You can just swap the backend that Noir actually has with it, which is called Burdenberg, and you can swap it with ProofKit. So currently this is in a development stage. We're planning to release V1 in a couple months, post-audit and all those sorts of good things. But it essentially allows you to build or create client-side proofs in a very performant way. So some of the constraints that we have around it is that it should be able to create a proof of a circuit that has up to 2 to the 24 constraints, which is 16 million constraints, which is most ZK identity applications out there, like ZK KYC, ZK Passport, and others, in less than a minute on a really low-end mobile device. So essentially, it gives you the ability to have privacy in the palm of your hands, right? In this case, meaning like mobile apps and mobile phones, which everyone has around the world. So this is the slide I'm going to get into a little bit more of the technical side of things, where you start with Noir. Noir is sort of the interface they use to interact with ProofKit. It's the programming language that many developers use in the ZK space. When Noir compiles into sort of this intermediate representation, essentially it allows the Noir compiler to have a set of opcodes that it supports. And it's the last thing that it's still in programming land before we go into ZK land. So we go into this Noir Acer intermediate representation, and then we convert to this thing called GR1CS. So R1CS is rank 1 constraint system. It's sort of a way to represent computations with polynomials. We call this an arithmetization scheme in ZK land. And GR1CS is a version of that allows us to have lookup tables for those who are ZK savvy. So the Noir Acer compiler will then compile to GR1CS. And from that, we're able to then work with these polynomials in ZK. So that's the second side of it. So we chose this proving system called Spartan, which was built originally or developed by the Microsoft research team, so Srinath Sethi and his team at Microsoft in like around 2019, 2020. And this proving system is really performant on the client. However, there was a few limitations around it, namely that the proof sizes were too big, some of the performance wasn't great, and the commitment schemes were not that performant that you could combine with Spartan. But recently, and last year, the team at EPFL in Switzerland developed this polynomial commitment scheme called WIR, which is inspired by a lot of like new literature in cryptography. And so combining Spartan with WIR gives you, in our opinion, like the most performance scheme when it comes to a proving system. And it's sort of like what the actual proof looks like on the client side. So ProofKit will generate the Spartan proof on the client, and then it will send it to a server. But now note that once you send this to the server, the privacy has already been achieved. Like you already get zero knowledge at the level of the client, and now you just send a not so big proof to the server, and the server is able to recursively verify multiple proofs into one Gross16 proof, which you can then verify on chain. And so this is sort of the stack that we chose that is sort of most performant. Another honorable mention is that we also are working on this implementation of a new hash function called Skyscraper, which is really ZK friendly. You may have heard of other ones like Poseidon or Poseidon 2, which have been historically used in a lot of ZK protocols. So a lot of the improvements that have happened there also led to development of Skyscraper, which we're really excited about. So this is sort of like the technical stack, right? Like I started with Noir, and I can get all the way to a proof I can verify on the EVM, on WorldChain, or any other L2, right? If you're an EVM developer, you can build your own verifier for any other L2 or virtual machine, whatever you want. Or you can also verify server-side in a Rust program or anything else. So what are the things that this actually enables from the application point of view, right? So the things that we're working on nowadays are personhood and NFC documents, which we call World ID credentials. Personhood is something that already works nowadays with our current proving system, which uses Gross16 and an existing set of libraries. But NFC documents is something that we're experimenting right now in beta for select countries. And this is where you're able to create proofs about your government identity in a fully privacy-preserving way, right? I can prove to someone that I own a government-issued credential like a passport. For example, me personally, I'm a Czech citizen from the Czech Republic. So I can create a proof that I'm a Czech or that I own a Czech passport and that the age in my passport is greater than 18, and then I can use that to access a website that is maybe like age restricted, for example. There's been like a lot of these issues with social media and adult sites and casinos and all these other things where it's been really hard to build it in a way where compliance and like regulations are actually enforced, but at the same time doesn't compromise the privacy of the user. You have regulations which tell the companies to essentially collect personal information about the user in order to verify that you're of a specific age, but at the same time you compromise the privacy of the user using that service for whatever reason, right? So like if I want to sign up to a social media site, I should be maybe over 16, and I should not have them I should not have to be made to like sign up with my like KYC document, right? I should not be able to, or I should not have to upload my passport or my personal ID to Facebook so that I can use that service. And over time, as this is going to be like sort of more important because of regulatory reasons, this is sort of like the way to do it in a fully privacy preserving way where the user is fully in control at all times of their personal information. Another thing that is really, really interesting, so these are the things that are already supported by World ID today and the things that we're rolling out, but where it's also really useful outside of the things that we're building is, for example, you've maybe heard like things of like web proofs. You can create proofs about any data that is on a website through these protocols that people call zk-TLS. So you have usually some client and server, right? So I have a browser, which is my client. I have a server like uber.com. And there's protocols like TLS Notary and others that allow you to intercept the traffic, the ciphertext between the client and the server. Some TEs on some multi-party computations service of multiple TEs able to sign that information, and then you can create proofs about that data. So I can create, for example, proofs that I've done more than 10 Uber rides, or the balance in my bank is greater than this. Maybe you've seen applications like ZK peer-to-peer, which allow you to do like a fiat on-ramp, off-ramp between the chain by just proving like Venmo transactions or Revolut transactions, and you can swap them back and forth. So this is all things that allows you to do because the client side, all of this is bottlenecked by client side proving, especially if you assume that the user doesn't have a flagship phone. A lot of the products that work with ZK today assume that the user has usually like really good hardware, but ProofKit will allow you to expand that top funnel by a lot. Another thing that is really useful is like on-chain proofs, right? Like imagine you have some state in Ethereum you want to create a proof about. Like I've interacted with Aave with more than 100 transactions and my collateralization ratio was always higher than this. You can do all sorts of proofs that are really useful when it comes to creating a general identity protocol on-chain or even off-chain if you care about privacy. Emails, right? I can create proof of email data. There's ZK email. You can go to zkemail.xyz. Where you can check out like how you can create a proof from like any email data. Like I've received an email from, I don't know, DoorDash that I've received an order. I can create proofs of that. Social graphs, right? I can prove that I know 10 cryptographers like follow me, for example, on Twitter, and that's like a useful signal so that I can enter like a cryptography forum, for example. Attestations, right? So there's protocols like Intuition and others where I can make, for example, a statement that like I think that Cristiano Ronaldo or Lionel Messi is like the best football player in the world. Currently, there's no way to figure out like what people actually think outside of just like knowing a lot of people, maybe making an opinion. But in the future, if anyone has an identity, people can make a social graph, and that social graph can start attesting to different facts, and you can now create proofs about those facts thanks to client-side proving. And there's many others like attested sensors. So imagine, for example, that this microphone would have a cryptographic chip, and the microphone at the end of the recording would just sign the recording, and you can create proofs that I actually said the things I said, because maybe if someone on Twitter posts a tweet and says that I said something I didn't say, I can actually make a claim, hey, I did not say that, I said something else, and here's the proof of that. Especially in the age of AI, this is going to be like very important because people can, or like AIs can fake the video, the text, or the sound, or anything else. So these are sort of like a lot of the tools that I think are going to be really important and sort of like the reason why we're building a lot of these tools. So in general, we're moving into a world where you can prove anything about everything as long as there's a signature associated with it. Of course, there's always like trade-offs between like what is the root of trust, like who is issuing the credential or the thing that I'm making a proof about. If it's a government, is the trust assumption of the government issuing the governing body issuing the document, or if it's the chain, you're trusting the chain for like having liveness and not having bad data, et cetera, right? So you're creating proofs about data, but as long as you have a root of trust from it. Another thing, which is the last touch point I wanted to talk about, is shared private state. So one problem in the modern like cryptography space is that if I want to create a proof about something, that data needs to be at the level of the client. But what about data that is shared among multiple people? How do I make sure that I can share data with multiple people and then create proofs about that, but the global public is not able to see that? So this is where techniques like multi-party computation and FHE are really useful, because these private blockchains that, for example, like like Aztec or Maiden, who are building these fully privacy-preserving programmable blockchains, really are able to have things that are private on the client level if there's only one client, but they have issues with having smart contracts with private state that is shared across multiple people. And this is one of the things that is really important if we want to onboard like institutions or like production applications where you want to keep state private, but you want to have multiple people have access to that private state. So this is, I think, like in my view, one of the most underexplored bottlenecks in this space, which I really recommend people to look into. And we, for example, built a multi-party computation system for anonymizing our uniqueness check when it comes to iris codes. I'm really happy to explain that later if you have any questions. But yeah, this is the content of my talk, and thank you for listening.